Welcome to Texas State University's Organic Chemistry 2342, Organic Chemistry 2. I'm your guide, Dr. David Urban, and we will continue with Chapter 12, Part 4, Alcohols from Carbonyl Compounds, Retrosynthetic Strategies. Okay, so now that we've learned in the last section that we can make primary, secondary, and tertiary alcohols from different reagents, let's think about how we would design an experiment knowing the product we want to create. And so by knowing the product we want to create and backing up to figure out which reagents we want to use, we call that retrosynthetic analysis. Okay, when we look at Grignard products like that, we can look for things that are symmetrical or unsymmetrical to figure out which reagent we want to start with. Okay, so to do this, what we want to do is start looking at where the carbon with the OH is, because the carbon with the OH is where our carbonyl compound was. And so we want to be able to start where our carbonyl is and then figure out which organometallic reagents are there. So for example, let's go ahead and draw just a generalized structure here of a carbon with an OH on it here. And we're going to draw an R1, R2, and R3. These could be any units here. So the first thing we want to think about is, number one, are all these R groups the same? If they are they are the same, then we can actually have a wide variety of ways to do the synthesis. But if not, we need to think about exactly how we need to split off one of these groups to generate a carbonyl compound with the other two groups on it. Okay. So let's go ahead and do this step by step with an actual molecule to see if we can figure out what to start with in our reaction. Okay. So let's go ahead and do the retrosynthetic analysis of 3-pentanol. Okay. So we have 1, 2, 3, 4, 5 carbons plus an alcohol here. Now remember, we have a hydrogen here. Okay. So first off, we're looking at this saying, oh, we have a secondary alcohol. Okay. When we have a secondary alcohol, that means we have to start with an aldehyde. Okay, so now we have to start with an aldehyde, but we have to break off one of the two carbon chains possible. Okay, so if we redraw this without the hydrogen on it, since we know we have to have a hydrogen, we can either break the chain on one side, or we can break the chain on the other side. Okay, we only need to do one because we are going to add one R group during our reaction synthesis. So in this case, what we'll do is we'll look at breaking it in that one place there, which gives us our, by backing up, we'll see that our carbonyl compound had 2 carbons on it, plus the carbonyl, and our organometallic reagents had 2 carbons on it, plus the organometallic reagent. Okay, so by looking at the different species and where to break them, we can back up and discover what that is going to happen. Now, whenever we do a retrosynthetic analysis, we actually want to say, well, let's make sure it's working. So if we took a reaction and did both of these, added them together, this nucleophile would attack here. And then when we quenched with water, we would generate that secondary alcohol from that species. So whenever we think about retrosynthetic analysis, think about which side of the system we want to chop off and how, whether or not they're symmetrical. Okay, let me actually do another one that's not symmetrical, or that is different than this, so that we can try another system. Okay. Let's do another one, and in this one, what we're going to see is we're going to start with a tertiary alcohol, but we're going to start with a tertiary alcohol that looks something like this here, okay? So if we think about a retrosynthetic analysis of this, we have a tertiary alcohol, so that means we need to start with the ketone here. And so we actually have a couple different options for doing this. we can cut the chain in this position here, which would give us a different ketone, or we can actually cut the chain here and give us a different ketone. So let's do it in two different strategies and look at two different methods. Let's look at that breaking with the blue line first here, okay? So if we're gonna cut that line there, the starting ketone has to have these two methyl groups on it, which means our starting ketone would be something simple like acetone, and that would mean that our bringer reagent would have to be our phenyl magnesium bromide, right here. But if we were to cut it instead at this site here, we could generate something that would look more like this ketone here, CH3, plus a methyl lithium reagent or a methyl magnesium bromide reagent. But the other thing we could do for this here is we could actually, because it's symmetrical, we can cut both of these off and start with instead an ester or acid chloride and generate a compound that looks something like this, plus two equivalents of methyl magnesium bromide. So any of these three sets of reagents can be used to create that tertiary alcohol with two methyl groups and the phenyl group. Okay, so it just goes to show you, based on where you break your molecule apart, you'll have different starting materials, but all three sets of starting materials will get you to the same product. Okay, so now that we see we can break these things apart and put them back together in a different way, let's talk about some of the limitations of the organometallic reagents. Okay, the first thing we have to think about in the presence of these organometallic reagents is that they are very strong bases and they are very good nucleophiles. So in the fact that they're strong bases, that means we can't have any kind of acidic protons present in our system, anything like an alcohol, amines, be they primary, secondary. Right here, we can't have anything that's a carboxylic acid because it'll deprotonate that. It can't even have anything like a thiol. Those would be able to deprotonate, and you can't have an alkynyl hydrogen available to be deprotonated because it's acting as such a strong base. Now, the other thing that you might not have realized is you cannot have a carbonyl compound you don't want to react. For example, if you only wanted to react one aldehyde versus the other aldehyde, or one ketone versus another ketone, you don't have that specificity. It's going to react on all of those depending on how much reagents you have. Okay. Now, it'll also react with anything with carbonyl, like amides, or even nitriles. Nitriles are just like protected amides. And in addition, you cannot react anything with a nitro group because the nitro has a partially positive nitrogen here, and the organometallic reagent will attack the nitrogen. Okay. So that being said, there is slight specificity on the system in the fact that you can react one group over another. For example, aldehydes will react faster than ketones, but it's very hard to use that specificity. Okay, the next thing I want to talk about is that you cannot do anything on these systems where you have a carbonyl group you want to attack, but you can't have any of these other groups present. So for example, if we had this compound here, and we wanted to react it with a nucleophile to attack just this thing using methyl lithium to give us our tertiary alcohol at the end of this chain, this reaction will not happen because what's going to happen is it'll deprotonate the alcohol and make it the salt, and then nothing else will happen in the reaction. Okay, so the problem with that is that sometimes we do want to react the carbonyl in the presence of another group. So how do we do that? Okay, we do that by using what we call protecting groups. Okay, so in the case of alcohols, alcohols are one of the most common groups that we protect. And we're going to show you a strategy for how to protect that alcohol so you can actually use those organometallic reagents to do additional reactions. So the first thing we do is we convert that alcohol group into something that does not have an acidic proton and will not react with a nucleophile. So in most cases, we do that by creating some other group like an ether that will not be reactive in that reaction species. Then we carry out the desired reaction using our organometallic reagent, and then we clip off the group that was protecting that alcohol, and that's called deprotection, okay? So one common route we use for this is we can protect alcohols by removing that hydrogen and creating a new oxygen-silicon bond. And we do that using an organosilicon reagent right here. Now, once we have this organosilicon bond here, we now have an ether. This ether, even though it has a silicon on it, is not reactive to the organometallic species because it doesn't have acidic hydrogen. Okay. So one of the very common groups we use in this book in particular is called T-butyl dimethylsilyl group. And so what that looks like is it has a silicon, 2 methyl groups, and then a T-butyl group here. And we use that group a lot because it is stable to a lot of different reaction environments, but we can easily remove it. Okay. So let's talk about what we would do with that. Okay. So for example, in that previous reaction where we had that ketone and that alcohol, and we wanted to just react the ketone right here, in our 3 steps we would try to protect that alcohol first. And in this case, we would use something like a chlorosilicon reagent. We're going to use that T-butyl dimethyl thing, dimethylsilyl chloride, and then we typically use it in the presence of a base to get it to go. So, and so we're just going to call this group right here our protecting group, and so it's only going to react with that alcohol at the end, protecting group, turning it into an ether that's non-reactive to our species. Then we can attack it with our methyl Grignard or any other organometallic reagent here. And that's, of course, going to give us our tertiary alcohol with our protecting group unaffected by the reaction after quenching. And then we're actually going to clip off that protecting group by some chemistry to give us our new desired product that we couldn't get to before, our new diol. Okay? So let's do this with an actual reaction. So let's go ahead and show you how we would protect and deprotect an alcohol. So we can take any alcohol here in the presence of a chlorosilane reagent, and we're going to use that same T-butyl dimethylsilyl chloride. And we typically do this reaction in the presence of imidazole, which is a base. In our reaction here. And that'll generate it'll take up the chlorine and generate a salt from the O here and the chlorine here, and it acts as a base to remove that. We'll end up with ORSI, T-butyl group here. Okay. Now the cool thing about this silyl ether group is it's very stable to a lot of different nucleophilic reagents. It doesn't react very well, and it actually increases solubility of a lot of materials. Okay. Now, one of the susceptibilities of this silyl ether is the fact that the silicon fluorine bond is a very strong bond. And so we actually end up using to remove these silyl ethers using a fluoride ion, such as this tetrabutyl ammonium fluoride. Okay. And the way that works is we take our silicon reagent here and we just put it in a typical solvent with our fluorine ion in it, and what we end up with is generating our alcohol plus our fluorine silicon bond that we can get rid of. Okay, so we can use that salt to regenerate our alcohol that we protected after we've done whatever other reaction we want to do on the rest of the chain. Okay, so that concludes our Chapter 12, Section 4, Reactions with Organometallics, Limitations and Protection Strategies for doing reactions on just the carbonyl compounds you want to react.